So the next thing is the dot product, how to get the dot product. So consider two vectors A and B such that the tails of both the vectors are on the same position, say 0, 0, 0. Let's say we'll go back to Maya and then we'll see the vectors A and B. So the vector A and B has a tail at the origin which is 0, 0, 0, and the vector A head will be on 4, 4, 0, as it has no movement in z direction. So the head of B will be 8, 0, 0 at its head, as because the movement of B is only in one direction, which is the next direction. So we can say that the magnitude of A will be calculated by the square of x component, y component, and z component. So 4 square plus 4 square plus 0 square will be 16 plus 16 will be 32, and the square root of 32 is 5.66. The magnitude of B will be 8 square plus 0 square plus 0 square, which is 64, and the square root of 64 is 8. So the dot product can be written as A multiplied by B is equal to magnitude of A multiplied by magnitude of B multiplied by cos of beta. So A multiplied by B will be, here is x component of A multiplied by the x component of B, and add on this the following components. So 4 multiplied by 8 is 32, then 4 multiplied by 0 is 0, and 0 multiplied by 0. So the A multiplied by B will be 32, so it can be written as 32 is equal to magnitude of A was 5.66, and then the magnitude of B was 8, so cos of beta. When we do a crossover, it will be 32 over 5.66 multiplied by 8, which is this, and then if you solve this one, it will be 0.706. So the beta can be calculated by cos inverse, which is 45 degrees. So the angle between both the vectors is 45 degree. One more thing is that dot product is also known as the scalar product. So you can see clearly that the angle is, if this is 0 and this is, if this is x and this is y, so you can see this is 90, but these two vectors are in place and the angle between them is 45. Now another way to calculate this by using the Lambert's law. So we can calculate the intensity of light source on the head of vector A. So the vector A is 440 and the vector B is 010, as you can see it over here. B has no movement in these x and z direction, and 1 unit movement in y direction, and same it goes A has no direction in z, so it's 4 movement here and 4 movement in y direction. So the magnitude of A will be, now we need to minus this to get this vector, 4 square plus 3 square plus 0 square, which is 16 plus 9, which will be 25, and the square root of 25 is 5. So the formula can be written as A multiplied by B is equal to magnitude of A multiplied by magnitude of B and cosine of beta. So A multiplied by B is 0 multiplied by 4, which is 0, 1 multiplied by 3, which is 3, and 0 multiplied by 0 is 0. So if you add it up, it will be 3. So it can be written as cosine of beta is equal to 3 multiplied by 5 divided by 5. When you divide this, you'll get 0.6. So the light intensity at the 0.010 is 0.6, the original intensity at 440 of the light at the head of the vector. So that's Lambert's law in Maya. So the next one is the cross product, how to get the cross product. So cross product is another way of multiplication which results in getting a new vector and calculate the normal of the surface. The new vector will be exactly the right angle of the surface from the two, which the surface formed by the two vectors. Let's say we will have these two vectors A and B forming a surface which has vertices of D, E, and F, and that's the vector which is, we are getting a result which is normal to the surface of these two vectors. So go back to here, vector A and B can be written as A plus AI plus BJ plus CK, and B will be DI plus EJ plus FK, where I multiplied by J is equal to K, and J multiplied by K is equal to I, and K multiplied by I is equal to J. So by multiplying these two vectors, it resulting in getting a vector C. So all the vertices, as I said, of the surface can be named as D, E, F. In this case, so the cross product can be written as magnitude of C is equal to magnitude of A multiplied by magnitude of B sine of beta. So remember, we use the cosine of beta in dot product, and cross product we use the sine of beta. So the cross product is also known as the vector product. So as shown in the viewports in the images here, that's the two vectors A and B. That's the perspective view, and that's the aerial view. And so vector C can be shown in the image below, which is exactly the right angle to the surface formed by the original vector A and B. As you can see it here, it forms, if you multiply these two vectors, you will get this vector here. Thing is to visualize the matrices. So for this, we need to do a translation or transformation. Having a cube at the translation of 0.5 Maya and a locator at translation of 111. We'll open up our Maya here. We'll get the cube first, which is, you can see it's 0.5, 0.5, 0.5, and the locator, which I already made, is on the layers 111 here. So you can see a cube and locator at its location. So now we'll do a translate by a factor of 4. Means x plus 4, y plus 4, z plus 4. So x dash will be 1 in x direction, then 0, 0 by factor 4. Y will be 0, 1, 0, and by factor 4. The same goes with z, and it's 0, 0, 1, 0, 0, 0, and 1. So once you multiply, you'll be 1 multiplied by 1 is 1, 0 multiplied by 0 is 0, 0 multiplied by 0 is 0, and 4 multiplied by 1 is 4. So you get 5. Same here, you get 5. So this viewport shows you the location of the cube and the locator. Now what we'll do, we'll move after getting the value. Now I have changed the translation value of the locator followed by the cube, which I moved manually. That process set the transformation for the matrix in Maya. Back to our Maya viewport, and then we have the locator and the cube. So what we'll do, we'll locate this locator first at by the value of 555. So let's say 5, 5, 5, sorry, 5, and here 5. So you'll see the locator here. Now what we'll do, we'll move this cube manually. So 2, 3, 4, 4.5, because 4.5, yeah, somewhere here, and then this direction 4.5, 2, 3, 5 here. Here, and 1, 2, we'll see now. So this is cube is exactly the same as here. So what we'll do, I can adjust it from here as well. Yeah. So you'll see the cube, and that's the transformation. The next thing is how to do the scaling. For scaling, what I'll do a scaling of a matrix in Maya. First I locate the locator at 2, 2 and the cube at 2.5, 2.5. Set the origin from the bottom corner so that I can scale it. So what I did actually, that scale is here. Now we'll switch off this layer. We'll go back to this layer. So we'll set is 2.2 first. That's our original matrix here, and now we are going to apply the scaling. We'll do the scaling of this matrix, of this cube in Maya. So that's the location showing here. So scaling the xyz by a factor of 2, which will be written as px is equal to 2, py is equal to 2, pz is equal to 2, px is equal to 3, py is equal to 3, and pz is equal to 3. Algebraically, it can be written as s dash is equal to sx plus px 1 minus sx. Y dash is equal to ssy plus py 1 minus sy, and z dash will be sz z plus bz 1 minus sz. So x dash will be 2, because we have this location at 2. It's 2, and then 0 for y value, z 0 for z, and then 2 1 minus which is 1 minus 2, sx is 2, so which comes up is result in minus 2. So once you get this y value, z value, you can multiply it's 2 multiplied by 2 is 4, 0 multiplied by 0 is 0, 0 multiplied by 0 0, 2 minus 2 multiplied by 1 means minus 2, which can be simplified that 4 minus 2 will be 2. Same goes here, same goes for the z value. Now for doing by 3, you will get 2 multiplied by 3 is equal to 6, 0 multiplied by 0 is equal to 0, 0 multiplied by 0 is equal to 0, and then minus 2 multiplied by 1 will be 0 multiplied by 3 is 0, minus 2 multiplied by 1 is equal to minus 2, so 6 minus 2 will be 4, same goes for y, and then z. So now what I'll do, I will set the scale of the cube 2 to 2 and then another locator. So as we get this, we have this value of 2 to 2 for the matrix, so we'll go back to our Maya, we'll scale this. So I already had a locator here, which is this one, and if you check the value, it says 4, 4, 4, the value of this. So the position will remain of this cube will remain the same, but the scale becomes double. It was 1 before, so that's the scaling thing in Maya. You'll see this in the viewport. Now the next thing is rotation. How to do the rotation? We'll go back to this. We'll switch off our layers. We'll open this cube and we'll set this cube at 0 now. So we will have these two locators. We save our scene. So the location is 0.5. This 0.5, and the scale is 111. So we can set our corner here. So we can rotate this matrix like this. We will do it here now. So this can be achieved by rotating an object in 3 dimensions about an axis or some arbitrary axis. Rotating an object from the orthogonal axis are also called as Euler rotations. Algebraically, it can be written as x dash is equal to x cos beta minus y sin beta. Y dash will be x sin beta plus y cos and beta. So that dash will remain z. There will be no movement in this z direction. So now the 3D transformation can be written as x dash will be cos beta minus sin beta 0 for z and 0 here. So sin beta for 0 and 0, and sin beta here, cos beta, just kind of know that cos 90 will be 0 and sin 90 will be 1. So 0 0, so z dash will be 0 0 1 0 0 0 0 1 xyz. So x dash will become, so cos beta angle is 90, but actually you'll see it's on the 90-degree angle for this locator. So cos beta will be 0, cos 90 will be 0, will be 0, sin 90 is 1, so minus 1, 0 0, same here, sin 90 will be 1, cos 90 will be 0. When you multiply 0 multiplied by 0, minus 1 multiplied by minus 1, 0 multiplied by 1, 0, 0 multiplied by, so it will be minus 1 and 0 and 0. And after rotating at 90-degree, let's say if we have this, we will rotate at 90. Sorry, we will rotate. We'll see it's rotating in Z at the moment, so we will set this 90. Save our scene. Go back to our document. After rotating at 90-degree, x dash will be 0 minus 1 0 0 because x y z x dash will be 1 y 0, that value 0 and then 1. So 0 multiplied by 1 will be 0 minus 1 multiplied by 1, 0 0, then 0 and 0. So it will be here 0. So 1 multiplied by 1, 1. So that's how you will get the 1 here. So it will be shown here so that you can rotate the matrix with the corner, and you can have another locator here showing that it's rotating from this point. So that's it for